Welcome to our exploration of data structures. Data structures are logical or mathematical models that organize data in specific ways to mirror real-world relationships and make data processing efficient. Choosing the right data structure is crucial. It must be rich enough to represent real-world relationships, yet simple enough for effective processing. Throughout this video, we'll break down the basics, introduce key terminology, and see how these structures are used in practical programming scenarios. Let's start by understanding the fundamental building blocks of data organization. Before diving deeper, let's clarify some essential terms. Data refers to values or sets of values. A data item is a single unit of value, which can be further divided into sub-items called group items or remain indivisible, known as elementary items. Entities are objects with attributes like a person with a name, age, and ID. Fields represent single attributes. Records are collections of fields for one entity, and files are collections of records. Understanding these terms lays the foundation for grasping more complex data structures. A file, each record may have a unique field called a primary key, which helps identify records quickly. For example, a student's ID number or an employee's SSN can serve as a primary key. Records can be fixed length, where every record has the same size, or variable length, where records differ in size. This distinction affects how data is stored and accessed, influencing performance and flexibility in data management. Simple organization into fields, records, and files isn't always enough for complex data processing. That's where advanced data structures come in. Studying these involves 3 steps: describing the structure logically, implementing it in code, and analyzing its memory and processing requirements. This approach ensures that the chosen structure is both effective and efficient for the task at hand. Data structures are generally classified as primitive or non-primitive. Primitive data structures are basic types like integers, characters, and booleans, directly supported by programming languages. Non-primitive data structures are built using primitive types and include arrays, linked lists, stacks, trees, and graphs. Non-primitive structures can be further divided into linear and nonlinear types, depending on how their elements are arranged and accessed. Linear data structures arrange elements in a sequence like arrays, stacks, queues, and linked lists. Each element has a unique predecessor and successor except the first and last. Nonlinear structures such as trees and graphs don't follow a strict sequence. Trees represent hierarchical relationships, while graphs model complex networks where elements can be connected in various ways. Choosing between linear and nonlinear structures depends on the nature of the data and the operations required. Arrays are the simplest linear data structures. A one-dimensional array is an ordered set of similar data items, each accessed by an index. For example, an array of student names or sales figures. Arrays can also be multidimensional, like a two-dimensional array representing a table of sales across stores and departments. Arrays are efficient for accessing elements by index but have fixed size and type, which can be limiting in some scenarios. Trees are nonlinear data structures that represent hierarchical relationships. Each tree has a root node and branches out to child nodes, forming levels. For example, an employee record can be structured as a tree, with group items like name and address further divided into sub-items. Trees are widely used in databases, file systems, and organizational charts to model parent-child relationships. Stacks and queues are special linear data structures. A stack follows the last in first out LIFO principle, where elements are added and removed from the top. Think of a stack of plates, only the top plate can be accessed. A queue, on the other hand, follows first in first out FIFO, like a line at a ticket counter. Elements are added at the rear and removed from the front. Both are fundamental for managing tasks, undue operations, and resource scheduling. Graphs are nonlinear structures used to represent complex relationships between pairs of elements. Unlike trees, graphs can have cycles and multiple connections between nodes. For example, airline routes between cities form a graph where each city is a node and each route is an edge. Graphs are essential in networking, social media, and transportation systems for modeling interconnected data. Data structures support various operations: traversing, visiting each element, searching, finding elements, inserting, adding new elements, deleting, removing elements, sorting, arranging elements in order, and merging, combining data sets. Mastering these operations is key to effective data manipulation and algorithm design. Each operation has its own algorithmic approach and efficiency consideration. C. Arrays are declared with a fixed size and type. For example, intlist5 creates an array of 5 integers. Arrays are stored in consecutive memory locations, and the address of the first element is called the base address. C also supports arrays of pointers, allowing for more flexible data management. Understanding how arrays are implemented and accessed in memory is fundamental for efficient programming. Structures in C allow grouping of different data types under one name, making it easy to represent complex entities like a person with name, age, and salary. Unions are similar but store only one member at a time, sharing memory space. This is useful when variables may hold different types at different times, saving memory. Both structures and unions are foundational for building more advanced data structures. Pointers are variables that store memory addresses, enabling dynamic memory allocation and flexible data structures like linked lists. Functions like malloc, calloc, realloc, and free allow programmers to allocate and manage memory at runtime. While powerful, pointers must be used carefully to avoid errors like memory leaks or invalid access. Mastering pointers is essential for advanced C programming and efficient data structure implementation. Polynomials can be represented in C using arrays or structures, allowing for efficient operations like addition and multiplication. Sparse matrices, which contain mostly zero values, are stored using compact representations like arrays of triples row, call value to save space. Operations such as transposing a matrix or adding polynomials become more efficient with these specialized structures, especially when dealing with large datasets. Strings are sequences of characters, stored as arrays in C and terminated with a null character. Operations include concatenation, substring extraction, and pattern matching. Pattern matching algorithms like linear and table-based methods help find substrings within larger texts. Efficient string handling is vital in applications ranging from text processing to search engines. Wrap up: data structures are the backbone of efficient programming and data management. From arrays and linked lists to trees, graphs, and specialized structures like polynomials and sparse matrices, each serves a unique purpose. Mastering these concepts enables you to choose the right structure for any problem, optimize performance, and build robust applications. Keep exploring and practicing to deepen your understanding and skills in data structure.